Hi, welcome to Signal Path. In this episode, we're going to try another repair. This is an Agilent E4433B, 250 kilohertz to 4 gigahertz signal generator. I may have done a repair of something like this similar in the past, I forget now, but the reason I picked this one off of eBay is because it's a really well-equipped unit. It has IQ modulator, dual baseband generator, high power and good crystal and so on and a bunch of other features built in it, which is great because it means it's actually worth fixing something like this. I don't buy the 3 gigahertz version of these anymore because I think we've already seen quite a few of them. So I'm trying to do some of the higher frequency ones. So this one is listed as not working, and again, I can buy these and bring these repairs to you guys because of my Patreon supporters. Take a look at the Patreon page. You can see updates and kind of the goals I have on there. I really appreciate the people who are supporting me on that. So let's go ahead and turn it on and see what happens. It's listed as non-working. So let's see. Let's see what happens. Now, these things usually take a little bit of time to boot. It has to do some checks on the firmware. The screen on these tend to be quite dark as time passes. These are cold cathode tubes. You can always change them, of course, and make them LED based. So I'm going to wait for it to boot up and see what happens. It's actually kind of the first time I'm turning it on myself. So I'm curious to see what kind of problems it has. And well, here it is. It seems like it booted no problem. I hope that the screen is not flickering because sometimes it can be synced or be very close to the refresh rate of the camera itself. I'm going to change that and hopefully this would be better. Okay, so right now you can see that it did boot up. It actually had an oven cold warning here initially that went away. That's normal because it does have an oven controlled crystal oscillator and it warns you until it reaches temperature, and then the frequency is essentially stable because all the frequencies of the instrument are derived essentially from that 10 megahertz crystal. And if you take a look at the block diagram, I will go over that with you. So it seems like it's okay. Let's go ahead to 1 gigahertz, let's say. Now, all of these instruments have a series of bands of frequencies that are treated a little bit differently. So sometimes you could actually have a problem at, let's say, 250 megahertz, but then have no problem at all at 4 gigahertz. So we have to check that. Let's go ahead and set the amplitude to 0, which is, I believe, the highest level where all the attenuators are turned off. And let's go ahead and turn it on. Yeah. It's not giving any error. Normally, it would say on level, for example, if there is a problem with the ALC circuit or if the signal generated is actually not being detected by the ALC. So that seems to be, interestingly enough, okay. Let's go to 1 megahertz frequency. And yeah, it doesn't seem to be doing any problems. Let me go back to 1 gigahertz, and let me increase the amplitude and see at what point we're going to actually get the on level. There you go, I can hear the attenuator just turned off completely. So, even 18, 19, wow, 20 dBm. There it is, 22 dBm, and we're getting on level, which is, I think, about correct for this instrument. So, that seems to be okay. So, what's wrong with it? I think I'm going to have to connect the output directly to a spectrum analyzer and find out if anything's coming out of it. Maybe it has some problem that cannot be detected by the ALC circuit. So I went ahead and preemptively took the cover off and the top off because I have a feeling we're going to have to get into it because I did a very quick test on the output. And let me show you what I see. So I have it set to the same thing, 1 gigahertz 0 dBm, and I have it here connected to my Keysight MXA. So let's zoom in, look at the screen and see what happens. So let's enable the output of the synthesizer. It's set to 1 gigahertz and an amplitude of 0 dBm. Here we go. And we're getting minus 23 dBm. So, well, that's obviously incorrect. So we're down about 23 dB or so, maybe about 22 dB. There's some loss in the cable too. Let's try a couple of different values and see if we can identify where the problem is. Now, remember, the ALC circuitry is not giving us an error, and the frequency is correct, 1 gigahertz. That means that the PLL is working, and that's not surprising either, because if the PLL was unlocked, the instrument would also warn you about that, which it isn't. So that's all good. Let's go ahead and go down by 10 dBm. There you go. You can see it went down by exactly 10 dB. Another 10 dB. It went down by another 10 dB. Let's go above. So here's back to 0. We're going to now to 10 dBm. Ah, look at that. At 10 dBm, it is giving us the correct value. That almost certainly indicates that the attenuator is the problem because this has discrete attenuation. As you've seen, I've talked about attenuators and I've shown you what's inside them a couple of times already. And when you go to 0 dBm, all the attenuation circuitry must be bypassed, and that's why we're getting the right value. So one attenuator block is broken. We're going to have to take a look at that. But aside from that, we should nonetheless take a look at the block diagram of the instrument, just so we can understand what's going on and why an attenuator problem doesn't show up in the ALC circuitry, and in general, how all the PLL loops and various blocks are connected to each other. And then we can come back and take a look at the attenuator. So here's the block diagram of the instrument. This is highly simplified, but it should still be enough to get the point across. As you can see, it's divided into a few important sections. We have the synthesizer board, which is responsible for actually generating all the carrier frequencies that the instrument puts out. And although it's really, really tiny, but here it says 250 megahertz to 4 gigahertz. So that's almost a full range, and below 250 megahertz, some other outputs need to be used. So we also have a reference board. This reference board is where all the frequency PLLs are derived from. That's where the 10 megahertz PLL is right down here. There's also 1 gigahertz PLL, which is locked to the 10 megahertz PLL for the higher frequency functions. Now this instrument does have the baseband generator board. This is where all the digital blocks are, with an IQ DAC with various filters, which are then fed into the output board, which has an IQ modulator, which is completely calibrated, and there's some routine that you have to run to do the calibration. You can see I and Q gain and offsets are set over here. So all of that makes sense. We also have various filters, of course, to get rid of the harmonics, because as you can see, the synthesizer board generates many of the frequencies by using division and multiplication, because they don't want to have a Yig oscillator, which is over here, that covers the entire frequency range. They only want to cover a set of range of frequencies. I'm not sure if this is actually a Yig in the one that I have, but I believe you could also have a Yig reference in this one. So, and then there's a bunch of other circuitry to do other kind of down conversions and multiplications and so on. We're not going to go into details of that, not that important. What is important is that the ALC circuit is right here. So as you can see, the ALC circuit has a feedback that comes over here, which levels the amplitude of the synthesizer itself. And that's really important. And because there is a feedback over here, a shunt type feedback, essentially, the output impedance at this node over here is zero, almost zero, depending on the gain of the feedback network, of course. That's why there's a 50 ohm series resistor here to match the output of the output board to 50 ohms. And then once it leaves the output board here, then you have absolutely no knowledge of what happens after this. There's no circuitry to detect whether the signal level is present and whether there is any problem or not. All the errors are generated from all the signals that you see over here. And of course, that's obvious because the attenuator and the RPP, which is reverse power protection blocks, are after the output board and therefore invisible to all the circuitry that are in there. But the block diagram gives you a nice high-level functionality of what's actually going on in the device, broken out into logical components, and they also translate to different boards in the unit itself. And when we're going to take a look at it, we will find out what it looks like. So we have to take a look at the attenuator RPP block and see what the problem is, and take it out and examine it and see if we can find out why there's a 20 dB extra attenuator in it. But everything else seems to be working, which is great, which means it just probably has only one problem. But to be completely sure if we can fix the attenuator, we should do further tests on it to make sure frequency accuracy is good, to make sure I and Q modulators are working, because that's one of the very valuable parts of this instrument, and we can do all of those tests afterwards. So here's a look from the top of the unit. Now underneath this, there are a couple of boards which are actually labeled over here. So our output board, our reference board, and our synthesizer board are down in here. Now we know that they most likely don't have any issues, so we're not going to take them out. There's really no reason. We have to focus on the part where we know there's a problem. So if you look at here, this is the output of the output board. That's where the signal from 250 kilohertz all the way to 4 gigahertz is generated, which is then fed into the attenuator block, which is right down there. The output of the attenuator block taken out here is fed to the RPP, reverse power protection unit, which has diodes and so on that detects any reverse power being fed into the unit. Now, normally in the industry, when people are testing these things, they may be connected to LTE amplifiers or some really high power amplifiers for cellular applications. And if they're not careful, sometimes a lot of power may come back into the unit from the output port, and you're going to have to find a way to quickly disconnect everything from it so that you don't damage all the other circuitry. And that's what this block is doing. That's why it's sitting between the attenuator as the last block and the output port of the instrument. So the output port of the instrument comes over here and goes directly into the RPP unit itself. Now, I don't think the RPP unit is a problem because we are able to get the correct output power at some certain attenuation, which means that the problem almost certainly is with the mechanical attenuator itself. Now, whether that has been damaged because of too much power coming back and the RPP not having enough time to respond to it, I'm not sure. But there is a log in the instrument that tells you how many times this has been triggered, and it will tell you how many times it's been tripped because of power coming back into it, and that gives you an idea of potential problems for the unit. I haven't looked at that yet in this case. So now we have to find a way how to take this out and take a look at it. We don't have to actually completely take it out. We could potentially just open these and pass a signal through it and measure it as parameters across different attenuations. But we know already that it has a problem. We know that one of these levels isn't working. So we can just go ahead, take it out right off the bat. And these things are driven with a standard attenuator control, which I can do outside of the instrument. I don't even have to have it in there. So let's go ahead and figure out how to take it out, and we can take a close look at it. Oh, and I also forgot a couple other things. Here are the baseband actually baseband ports, and the IQ modulated signals, the baseband IQ, are fed into these units through here from all these cables that you see. The motherboard's at the bottom over there. It has all the processors and memory and all the other things that are required to bring a system like this up with its own embedded operating system, of course. I don't see a Yig oscillator in here, so probably either doesn't have one, or if it has one, actually no, I wouldn't even see it in here anyway. It would be on the synthesizer board. So I'm not curious. I may also take the synthesizer board out just so we can take a look at it and do some analysis on it at least and see what it looks like. But one step at a time. Let's take this guy out. And here's the module out. Now we can go ahead and separate the RPP from the attenuator itself. So it should be just a few more disassembly steps. And then we're going to have to go ahead and completely disassemble the attenuator so we can see internal structure, and we can also see how many tabs it has and which one of them is damaged. And here is our attenuator. This is an Agilent E4433B-60014. This is a 135 dB total step attenuator, and I believe it said 5 dB per step, meaning that it has quite a few sections in there. It's going to have a lot of coils, and that's why it is so long. So we're going to take it apart and find out what's going on. One of the steps is most likely a 20 dB step, and that's the one that's damaged, and hopefully it will be obvious visually. And then how are we going to fix it? Well, I do have a lot of attenuators. I don't have exactly this one, but I may be able to find another pad and potentially replace it if the problem is simply with the pad. But we're going to have to take it apart and find out. So here is the attenuator. I've already taken it apart, and I've taken a close look at this. Now here's the attenuation segments themselves. You got to be quite careful with these things. Now I've already shown these on camera under the microscope from different repairs that I've done in the past, and you can go ahead and see my other videos to find out exactly how these look like under the microscope, how they work, how the resistor is deposited, what kind of substrate is used, and all of that. And simply, they are basically either contacted or not contacted. If you don't contact them, there's a through pad that doesn't apply the attenuation, or if you do, then you see the attenuation. And I believe this is divided in 5, 10, 20, 40, or 10, 20, 40, and 80. I have to figure out exactly what the attenuation steps are. Is divided into those sections. So we can go ahead and put this aside because I looked at it under the microscope and I couldn't find any issues with any of these pads. So luckily we don't have to worry about this. This can only mean a few things. It means that either something's wrong with the solenoids, which I don't think is very likely because we can get rid of the attenuation and get the correct output. That means that most likely we simply can't contact one of those pads very well. Now the pads themselves look nice. It means that one of the pedestals and one of these contacts here are the issue. So I hooked it up back to the instrument, and this allows me to be able to control the attenuator directly from the instrument itself. Now I'm going to try and awkwardly hold this and turn the attenuation, and hopefully you can see it. You can see them moving around. Like this. You can see the different pads go up and down as I increase the attenuation. So we can find out which of them is not working. If I go all the way to the end, you can see they're all pointing up. It means that all the attenuation is going to be used here. If I go back, you can see all the way at the end, none of them are going to be engaging. So in this configuration, it's working. And this simply means that one of them is not contacting the pads very well. So I'm going to go ahead and write down over onto the solenoids themselves what attenuation is what, and we should be able to figure out which one is not working. And hopefully, maybe it's just a minor repair, and we can put it back together. Okay, here we go. I have labeled all the attenuators in dB so that we can observe their movement, and I'm going to increase it until the 5 dB attenuator kicks in. So let's see what happens here. There it is. You can see that's the 5 dB attenuator. If I keep going, then the 10 dB will come in, and then the 5 will join right after. So that's the 15 dB attenuation. But if you look closely, you'll see that the little contacts are actually not at the same height, and I feel like that might be the problem with the 5 dB attenuator contact. It's hard to see. But if you look over here, the height of here, this pin, and the height of this is not the same. So this is going to have quite a bit of a hard time contacting the attenuator pads than the other one on the right side would. So this might explain our extra attenuation there. You can see if I just bend it over here, you can see the tip of the other 3, but you cannot see that one. Certainly much lower. And if I increase the attenuation until all of them kick in, the one all the way on the right side, you can see it's actually better. There it is, I think. Where is this? Everything is almost everything. And you can see even this one is a little bit lower than it should be, but it's better than the one on the other side. So I'm just going to go ahead and readjust this very simply and very carefully. You can't obviously pull on this very hard, they will snap. And the surface you cannot touch. You have to kind of push it from the bottom, otherwise it's going to get damaged. So I'm going to clean this up, fix it, and put it back together. And I wonder if that's going to make a difference. And if this is the only problem, that's actually pretty nice because it's an easy thing to fix. And then we're going to take a look at some of the other boards. So after some closer examination, it turns out that the little plastic rods that move the pieces of metal up and down that make contact with the RF traces, one of them seems to have a problem. So bending the metal is not a good idea, so I haven't done that. And we have to remove one of these solenoids in order to get access to it. And unfortunately, they are all soldered after they're assembled to the electronic control PCB here, so I have to take that off. So I unsoldered all of that. And we're going to take the 5 dB attenuator off and see where the problem is with the plastic rod that has that issue, and hopefully we can find a way to fix that. So here's a look at the problem. Now I don't recommend taking this apart any more than this, because you would have to actually remove the metal strips, and there's no way that's going to go back together the same way. It has a jig that needs to be there to put it together. But if you look closely, you can actually see the problem. So if you look, you can see those tiny plastic rods. That's what pushes in and out and moves the metal strips up and down and makes contact to the attenuator pads. And you can see the one all the way on the left is not at the same height as the other one. Therefore, it cannot push the strip all the way down. The reason is because each of these have a little tiny plastic ring that's a washer that's above and below the metal plate of the solenoid, and that kind of is there to dampen the movement so it doesn't strike the attenuator really hard and then ages it and essentially scrapes off the surface over time. But those metals seem to be deteriorating, and one of them has completely fallen off, and therefore the pedestal cannot move as much as it should. And I had a little tool here. You can see I can actually press it into place like so, like that. So you get that movement. That movement should not be there. It should be right over here. So when they're actually failing all over, they all have little cracks in them. That means that this is going to fail at some point. So what is the solution? Well, there's no way I'm going to be able to find those little strips, and even if I did, I would have to take it apart to put it back. So what I'm going to do is I'm going to make a compromise. I'm going to put some kind of flexible epoxy at the interface of all of these to the metal plate itself, and let that dry. And that flexibility will give you some protection and dampening, but it would also at least make the whole thing work. It may not be as good as obviously a new one, but it will certainly fix the attenuator and hopefully bring it back to life. Now the question is, how do you do that without getting glue everywhere else? Because there's a really tight space. If you get the glue in any other moving parts, because remember these plates have to go up and down like so. So you can't really put glue anywhere you want, because otherwise it's going to basically get stuck. So I'm going to see if I can do this somehow without damaging them. I'm going to apply the glue to all of them because they're all going to fail anyway. And then see, we put it back together. And if it survives, that'll be a nice little repair. If not, then we'll have to throw away the attenuator. So the attenuator is all back together. So before we put this in, I'm going to show you the RPP block. Now, I have already shown a lot of the other blocks in this instrument in the different videos, so you can go ahead and see how the synthesizer portion and the output driver portions actually work. But we've never opened one of these on camera before. So I wanted to tell you how it works and what it looks like on the inside. So here it is. Let's go ahead and zoom in onto this and do a little bit of analysis on it. So if you look inside of this, you can see that it's not very complicated, and it shouldn't be that complicated because it's all it's indicating is a high signal condition. So here we go at the output, we have the RF output port, and here is the RF input port coming directly from one of the cards inside the instrument. And as you can see, there is our main switch here. This is a relay, an RF relay. This is not solid state, it's mechanical, and even though mechanical ones are going to be quite a bit slower than a solid state relay, and its response time is going to be much worse, so therefore there's more danger of any damage happening. But this is so much more linear and can handle so much more power. It's just a solid state relay would be too difficult to put here. So you can see we have our relay, we have our two ports of the relay that turn it on and off. We have an AC decoupling cap there. You can see 3 capacitors vertically stacked to minimize their footprint and provide still a fairly good value. It's an interesting configuration there. And then you can see 2 diodes, one over here and one over here. Then you can see they are basically backwards with respect to each other. This is just a detection, a peak detection circuitry. So this measures the peak power that is present at this node. And when this relay is closed, any power coming back over here, whether it's DC, although the DC is blocked over here, but the AC power coming over is going to trigger these. And once you have sufficient enough power basically coupled into this, you're going to rectify that, and a DC voltage will appear either on the positive or the negative side. And then you have some detection circuitry and a trigger to basically flip this and then send the signal back to the instrument that it has tripped, and you can then reset the relay. So this is a very simple and useful block to put there. Now the disadvantage of something like this is its insertion loss, the impact it has on the return loss of the instrument, and just maintaining a good constant impedance across the entire region here. This board basically has nothing but loss, and nonlinearities adding to the output of the synthesizer. Especially these diodes are of course going to have some nonlinearity associated with them, especially since this instrument wants to do complex modulation, and we will see that. But nonetheless, this is very important, and it can protect the instrument against reverse power. So there it is. That's what it looks like on the inside. Let's put the whole thing back together. Okay, now closing everything back up, and one thing that's been really helpful in opening and closing all these microwave modules, because they have 100 screws, is this Hitachi screwdriver that has torque limit, which is really useful because you can set the torque over here, and then you can find out what is the best value, of course, depending on how much you need to tighten things, and it just makes working on all of these things so much faster, and I've been really quite happy with it. You can see it's really easy and fast. So I'll put a link in the description in case you want to buy one of these. I tried a couple of them, and this is the one that I've liked the most so far. Okay, let's give this a try and to see if it has fixed the problem. So I've connected an Agilent E4433B directly to the RF output port of our synthesizer. This allows us to have a measurement plane which is directly at the port of the instrument, which is what you want. So no cables, nothing like that, and we can measure power much more accurately this way. So the unit's already been zeroed and called and everything. So let's go over here. And what do we see? There it is. There's our power meter. You can see it's showing minus 46 dBm. It's going to go up and down by a few dB. At this range, it's within the uncertainty of the power sensor itself. I've also done an extensive video showing you exactly what's inside a power sensor, how it works, how the whole thing actually does power detection. You can go ahead and check that if you want. So right now I have the unit set to 1 gigahertz and 0 dBm. Let's go ahead and turn it on and see if it works. And there it is, and look at that. That is really nice. Right now it's about 0.09 dBm. That's very good. Remember, this unit is old. It hasn't been calibrated for a very long time. There's also some uncertainty from the power sensor itself because that also hasn't been calibrated. But this is really good. This is pretty close to what we would want. We can actually increase the power to higher power. Let's see. Let's go ahead to 10 dBm. Oh, that's minus 10. There's 10 dBm. There we go. That's pretty good. And 20 dBm. Also good. It's a little bit too high at 20 dBm, but it looks pretty good. Remember, anything above a few dBm is all electronic control. There's no mechanical anymore. But now we can engage the mechanical attenuators and to see if they're working. So here's 10 dBm, here's 0 dBm, here's minus 10, minus 20, minus 30. It works very well. I'm quite impressed with how well the attenuators are actually still working. So it looks like it's all good. We can also make sure that the 5 dB attenuator works by changing this by 5 dB at a time. I'm putting a value of like minus 15 dBm, and you can see this takes a bit of time to settle. That is not from the instrument itself, that's from the power sensor, as I have explained in the other video. So that looks good. That means that the attenuator is fixed. The question is it actually working, and its modulation and all the other functions are working, because that's what makes this unit really valuable. So there's two other tests I wanted to do, just to take a look at its frequency accuracy with the Rubidium standard, and then doing some modulation, just to make sure that works also, and that would be it. And here we have the unit connected again to a different unit instrument. Right now it's connected to a Fluke PM6685R, and this is a frequency counter calibrated. It's based on a Rubidium standard that's inside. I've done a repair on one of these on the channel and I talked about how it works. So at 1 gigahertz, let's see how accurate our source actually is. I'm going to turn it on. And what do we get? Not too bad. This is about 65 hertz off or so from what it's supposed to be. That's not too bad considering how old the instrument actually is. Now, one of the disadvantages of this type of synthesizers, which most synthesizers actually are, is that they achieve higher frequencies through multiplication. And I've gone through the block diagram so you can anticipate what that would be like if you were to multiply the frequency. So if you're off by about 65 hertz at 1 gigahertz, because we're multiplying it, our error in absolute value is going to grow. So if I go to 2 gigahertz, you can see that now we are off by exactly twice as much, about 130 hertz. And that's to be expected. This is what you would get when you do frequency multiplication. But the architecture of achieving 2 gigahertz from a 1 gigahertz source now becomes a lot easier, of course. But that's normal. That's how it works. So now really the only thing we haven't tested is some of the modulation functions. Of course, there's a lot more to do. But for us, if we get the modulation working, then we're fairly satisfied that the instrument is good. Before we do any IQ measurement and any modulation measurement, let's do an IQ calibration. And if this thing succeeds, this itself tells us that the internal measurement capability and calibration routines are actually working. So that's a good one. Let's wait for this to finish. So the calibration ran just fine. Let's go ahead and analyze a modulation with this instrument. I have a carrier set to 2.5 gigahertz, amplitude is 0 dBm. we're going to take a look at a 256 QAM modulation, single carrier. That's 8 bits per symbol, of course, at a symbol rate of 6.25 megasymbols per second. That's the highest this instrument can do at this modulation rate. So that's still quite a bit of data coming out of this. And then we're going to do a filtering of 0.35 root raised cosine. What else is important here? We're also going to have a PRBS sequence of 2 to the 31, 2 to the 23 minus 1. So everything looks good. Now, how do we analyze the modulation? Well, there are many ways we can do it here in the lab. We can use an oscilloscope. We have plenty of those. We can use either the Keysight or the Roden-Schwarz or the Tektronix software. There's a lot of those I've shown it, but today we're going to use a completely different instrument. So let's go ahead and use an Aeroflex SVA6 250 kilohertz to 6 gigahertz signal analyzer. This is a dedicated signal analyzer. I believe it can do up to about 160 megahertz of bandwidth or so. Right now it's set to a carrier of 2.5 gigahertz as we would expect. So we can go ahead and turn the carrier on and we should see a tone. And there's our tone. Looks good. That's what you would expect. And of course we can go ahead and turn the modulation on and we should see the modulation right around our carrier. So that also looks very good. Now we can go ahead and actually display the Constellation and see what kind of EVM we're getting from the unit. Okay, let's give it a try. So I'm going to change the result to looking at the modulation. And you can see I have set all of these things here. That's what we would expect to see. Let's go back home over here. And let's go over here and change our measurement to a trace measurement of Constellation. There we go. And look at that. That looks really good. Now I'm going to have to figure out how to zoom into this. And here is the zoomed in version. This is 4096 symbols being analyzed at one time. And look at that. That's a really nice and clean sequence there. Of course, we don't know any information yet. We're going to have to look at some of the data, and we're not doing any bit error rate. But just looking at how confined each of the modulation Constellation points are, I think that's going to be pretty good. And here's the data associated with that. So we have an EVM of about 1.3% or so. You can do equalization on this, which I haven't done. This is raw data uncorrected. And you can see, of course, magnitude error is almost completely non-existent. Phase error is non-existent. It's very, very well matched in terms of IQ. Of course, the clock of the analyzer and our source are not locked to each other. So they're free running. That's why there's phase error, and there's going to be present unless we lock the crystals together, which I haven't done over here. But other than that, I think it looks pretty good, which meaning that the modulation functions are all working just as well. Yeah, so there you have it. I think everything is good. I hope you enjoyed this repair. Again, this is thanks to my Patreon supporters that we can bring these type of instruments for repair and show you how it is going on. So please check the link description if you want to buy one of those screwdrivers. I think they work really well. And if you want to join the Patreon supporters, I'd really appreciate it. There'll be more equipment giveaways. I have to still announce some of the ones that I'm going to give away. So please stay tuned with that. It's just been really busy. And I'm going to see you in the comment section.